Hey, it's Troy here, and welcome back to the next in the series of creating new cards for my HBC 56. Today's video is covering the RAM-ROM card, which doesn't sound too exciting, but it does have a few features and tricks up its sleeve, so you might find it quite interesting. Once again, I'd like to thank my sponsor PCBWay, who has provided all of the PCBs for this part of the series. So thanks PCBWay. So before we get into the schematic, I'd like to first cover how memory is addressed on this RAM-ROM card. Now only 64 kilobytes is visible to the 6502 at any given time, but this card has provision for 64 kilobytes of RAM in addition to 32 kilobytes of ROM. So how we achieve this, the card is divided into two banks, named Bank 0 and Bank 1, with Bank 0 containing a single 32 kilobyte SRAM. The card can be configured in such a way that Bank 0 can be assigned to the lower 32 kilobytes or the upper 32 kilobytes of address space. For a 6502, obviously it makes sense to have this configured to the lower 32 kilobytes, but if the card was used in let's say a Z80 for example, you would want that reversed, and that's easily achieved. So Bank 1 is where the added complexity comes in. Bank 1 has provision for both a 32 kilobyte ROM and another 32 kilobyte of RAM. So how the bank's 32 kilobyte of address space is divided up between RAM and ROM is determined by a single 8-bit register. Each bit of the register determines how a single 4 kilobyte page is configured. If the bit is 0, that 4 kilobyte page will be assigned to ROM. If it's 1, it'll be assigned to RAM. So the register can be changed at runtime, so we can set each of the 4 kilobyte pages to RAM or ROM as required. Now I'll just go over a quick example showing how some of the addresses are decoded and assigned to RAM or ROM. So let's start out with hex address 6000. Now we first take a look at the most significant bit, and in the Bank 0 low configuration, which is the one I'm using for 6502, that means this address will be served by Bank 0. Simple enough. Okay, so now let's look at hex 9000. So again we examine the most significant bit, and we see it's a 1. So in this configuration that means Bank 1. Then we examine the Bank 1 page register to compare its bits 12 through 14 of the address, and we can see we're looking at a value of 1 on a 0 to 7 scale. That means the second bit of the register. So here that bit is a 0, so we pass that request on to the EEPROM, and if that bit was a 1, we'd be accessing RAM instead. So when it came time to choosing a register, obviously there's a bunch of options, but I needed one where I could have a known state at startup, and so I looked at the 273, which includes a clear pin, and that will set the entire register to zeros, which is good. And as we saw previously, that means that by default the entire Bank 1 will be looking at ROM. As you'll see in the schematic, I'll connect this to the reset pin so we have a known state at startup. So next I'd like to go over the schematic. As I described earlier, it's broken into two banks. So we've got Bank 0 and Bank 1. As you would expect, Bank 0 is quite simple. It's literally just the SRAM. So Bank 1 can be quite simple too. It's possible to just have the ROM and omit all of the logic related to the Bank 1 paging, including of course the RAM. So it is possible to just have the RAM chip, the ROM chip, and this NAND gate to handle the logic of selecting which one at what time. However, that's not very interesting, so I'll cover the full design for Bank 1 as well. So as I alluded to in the intro, we can configure this to have Bank 0 low or Bank 0 high, and that's just done with this single jumper here, and the result of that is passed into either the NAND gate or this GAL. The I/O GAL is basically required if you're doing banking, if we have bank control on. Otherwise we can get away with just this NAND gate. And none of these chips here are mandatory. So we've got the bank control GAL as well, and the register to control which page is either RAM or ROM. So in the basic configuration, I'm just using two of the gates for just inverters. So first we take A15, which is used to select either bank 0 or bank 1, and invert that, and then that gets passed through this jumper, and whether A15 or inverted A15 is chosen, that comes back to the NAND gate just to be inverted again, and that gives us bank 1 enable. So in the complex configuration where bank 1 we can have full control over whether it's RAM or ROM in 4 kilobyte chunks, we use a GAL to do the initial I/O decoding for that. So we take in the I/O request line, read, which we're basically using to know when to write, A15, so that gives us the bank 0 or 1. These lower address bits here are used to determine when we write to the bank 1 register. So in addition to that, it produces inverted A15, as well as bank 0, bank 1 enable, and the register enable here. Now the bank 1 control, basically it will look at this register, and so each of these bits comes out here, and they become inputs into the bank 1 control. And of the address line that comes in, we're only interested in address line 12 through 14, and we'll basically do a comparison of that value to which bit we're interested in, and based on that we'll enable either RAM or ROM within bank 1, which will become this one and this one. So the ROM can also be configured. We can handle multiple models of EEPROM. So that's what this jumper here does. So we can handle a 28C256, or a 27C256 or 512, or a 27C64 8 kilobyte ROM. And it handles that by manipulating here pin 1 or pin 27, depending on the specific EEPROM. So one thing I didn't cover in the CPU video was the GAL PLD. How do we program those? How do we make them do what we want them to do? So I'll do this for the this RAM-ROM board, since it has two of them. So I use the Atmel software called WinCouple for Windows, and you create a definition file, a .pld file, which defines the various pins and what behavior, what logic you want for them. So here we'll look at the RAM I/O PLD definition, and so on the right I've got the the chip layout showing which pins do what. And so first there's just some header information to define which device you're compiling for, you know, date and codes and whatnot. And then I do the input pins. So it's just a matter of looking at the input pins here and matching them in your definition file. So if we look at pin 1 here, you can see that's I/O request, and so I've just got not I/O here. So here I have logic low with a / prefix, and in the PLD file they actually take that into account as well. So if you have exclamation point for the pin name, it knows that's active low. And from that point forwards you can refer to I/O as being true, even though it's low, because it's true is active. So it's just a matter of doing this for all of the pins. So we've got IO, read, address 15, B0, and the lower address pins, which are used for the bank register, and clock in. And then we go and do our output pins. So we've got CW here, which is a combination of the clock and the write signal. So for writing, we only want to do it in the latter half of the clock signal, so while clock is high. A15B, so that's basically inverting A15. So this is doing the same role that the NAND gate is doing in the basic logic. And then we've got 17, 18, 19. So these are our various enables. So we've got BRE, which is for the register, B1E, which is for bank 1, and B0E for bank 0. And then some common logic. So the bank register, we can define what the address is here. So IO, I have a separate pin for IO. And so when that is active, as well as when these address pins are low and this one's high, which results in an IO port of hex 08. Then bank 1 enable is the inverse of bank 0. Write, the same thing, inverse, and memory is the inverse of IO. So we're either accessing memory or IO. Chip write, so that's the clock in and write, needs to be both high at the same time, or active, sorry, at the same time. Then we've got another invert. And so the register enable when we're writing and we're matching this port here. Bank 1 enable when we're accessing memory and bank 1. And bank 0 when we're accessing memory and not bank 1. So now I'll switch to the other PLD. Yep, so this one here, and find it. Okay, so same deal. So pin 1 is the chip enable, which is bank 1 enable. Then pins 2 through 9 come from the register, so they're saying which of the 4K pages are RAM versus ROM. So other inputs address 12 through 14, so they determine which of the pages we're currently looking at. Pin 14 is the write signal. This is another interesting one. We're actually putting a signal out to then read it back in again, and the reason for that is we don't have enough gates within this PLD to do all of the logic I want in one step. But this works fine. The PLDs are quick enough where that's not an issue at all. And you can see it here where the inputs wired to the output. And yeah, the two, so ROM and RAM chip enable, that's the ultimate goal of this. Each of these common logic values here are matching one of these input bits and which address needs to match for that. And so that tells us when either the RAM or the ROM is enabled for that page. And then here we combine each of these. So you know, for the ROM enable, for instance, we want, you know, either this or that or that or that. Then the ROM will be enabled, and it's the opposite of that for RAM. One thing to note is, even if the page has ROM enabled, I've set it up in such a way that if you write to an address, it will still write to the underlying RAM, and that allows you to quickly shadow the ROM into RAM. So it's just a matter of iterating through the address range and reading and writing to the same address, and that will read from the ROM and write to the RAM, regardless of the register pointing to ROM. So that's just a bit of a efficiency thing. So when I've finished writing this definition file, it's just a matter of compiling it. And that was successful. And so then I go into my Mini-Pro, pick the type of PLD that I'm using, which is already here, and select the file, grab my chip, put it in, so here, and program. That's it. So now if we take a look at the PCB, so the previous two were like mostly auto routed, where this one I've gone and manually routed a lot of the lines, which makes it obviously look a lot neater. So I've still used a combination of manual routing and auto routing, and the way I do that is to manually route all the signals that I care about, and it's most of these which are going to be in parallel. And then once you've done that, you just auto route and tell it to route the nets which haven't yet been connected. Because we're using a ZIF socket, obviously you need to make a lot of room for that. So it's make sure you pick the right footprint. And also having these configuration jumpers, I like to put the details of what the jumper position will actually achieve right there on the silk screen, which makes it much easier to work with. Okay, so now it's time to order this PCB. So I'll go to PCBWay.com, quote now, and I'll go quick order PCB, and just add my Gerber file. That looks about right. This is a 4-layer design as well, so I'll just put the layer definitions in. Again, I want black because those black cards look really good, and that's it. And so then add to cart and complete the order, and we'll wait and see what we get. So again, it's time for the box of PCBs, and we'll pull out the RAM-ROM card and see how it looks. Yep, fantastic again, but you already knew that. Alright, so let's get building. So this video is getting a bit long, so I'll run this time lapse at 16 times speed, and we'll get through it quick. So now it's time for the ZIF socket, and I always find these tricky. The pins are quite thick compared to normal sockets, and they're on a bit of an angle, and it just takes a bit of levering to get it in. but we got there in the end. Okay, board's done. Let's clean it up and put the chips in and try it out. Okay, so I've burnt invaders onto one of my 28C 256s, so I'll plug that in and set the jumper for that model of EEPROM, and then we'll try it out. So I'll take out the old RAM-ROM card and put in the new one. Yes, okay, I can get used to this. Okay, so that works great. Okay, so I was planning on covering the Bank One paging, adding some 6502 code to work with that, but this video is getting a bit long, so I'll do that in a future one. And I'll also need to update my emulator, so if you're interested in seeing how I go about making changes like this to the emulator, let me know below and I'll do that. And also let me know if you'd like more coverage of the emulator in general, and I'll work some of that in as well. Okay, thanks for watching. See ya.